Good morning, dear students. Today we will discuss about the angle modulation. So, this is the topic of the principal communication subject. So, what is the angle modulation and what is the advantage, what is the disadvantage, and what is the working principle of angle modulation? So, in angle modulation includes both frequency and phase modulations. So angle modulation is the summation of both frequency modulation and angle phase modulations. So in frequency modulation, the frequency of the carrier is changed with respect to amplitude of the message signal. That is the frequency modulation. What in phase modulation, the phase of the carrier is changed with respect to amplitude of the message signal or modulating signals. Unlike AM, both FM and PM are nonlinear, hence much more difficult to implement and analyze. So modulation index for FM wave is given by delta equal to del f upon fm, where del f is the frequency of deviation and fm is the modulating frequency. The expression for the fm wave is also given by fm t equal to a cos in bracket 2 pi fct plus beta sine 2 pi fm t, and modulation index for phase modulation pm wave is given by m equal to kp em, where kp is the phase deviation and the modulation expressed for a pm wave is so fm, so wave of pm equal to a cos 2 pi fct plus theta cos 2 pi f mt mt. So phase modulation can be used to generate fm wave, and fm modulator can be used to generate PM wave as follow. So in first diagram, there is the message signal. That message signal feed to the integrator, and after the integration, the output of this integration is m integration of m alpha d alpha, and this signal also feed to the phase modulator, and output of this phase modulator is the frequency modulated signals. And in second diagram, the message signal is applied to the differentiator, and the output of this differentiator is the differentiation of the modulating signal mt with respect to time, and this differentiation and differentiate signal applied to the frequency modulator, and then output of this frequency modulator is the phase modulation waveform. So this is the FM and PM wave generations. So in this, here given different waveforms of here. So first waveform show the carrier signal or high frequency signal, and second one show the modulating signal or low frequency signal. Third one is the frequency modulated waveform, in which frequency is changed but the amplitude of this carrier signal remains constant. And next, last waveform, that show the phase modulated output waveform, in which the phase is changed in the carrier waveforms. So FM with beta is very less than 1 is called narrowband FM, and expression for narrowband FM ft equal to Vc into cos omega ct minus cos omega c minus omega m t plus cos omega c plus omega n into t. So phasor diagram of narrowband FM is given here in this figure. So this is the phasor diagram of the narrowband FM. Now FM with if beta greater than 10 is called bandwidth wideband FM. So for the wideband FM, the value of beta is greater than 10. So expression for wideband FM ft equal to J naught beta cos omega ct minus J1 beta cos omega c minus cos omega mt and so on. So function J and beta is called the Bessel function here. The spectrum is composed of a carrier with an amplitude J naught beta and a set of sideband spaced symmetrically on either side of the carrier at frequency separation of omega m, 2 omega m, and 3 omega m, and so on. Unlike AM, FM has an infinite number of sideband along with carrier. These sideband are separated from the carrier by frequency FM, 2 FM, and 3 FM, and so on. So this is the Bessel Bessel function plots for the different value of beta in this figure, and also there are different value of beta, and single and double underline indicate here in this table the number of harmonic containing 70% and 98% of the total power respectively. So by the Jan formula for bandwidth of FM system is given by bandwidth equal to 2 into delta F plus Fn in hertz. For low modulation index in case of narrow band FM, since 2 del F is very less than Fn, equation reduced to bandwidth equal to 2 Fn, and for wideband FM value where del F is very greater than 2 Fn, equation reduced to bandwidth equal to 2 del F. So average power in sinusoidal wideband FM given by Pt equal to V square J square beta upon R plus V square C upon R into J square J1 square beta and so on. So Pt equal to Pc J square beta plus 2 into J1 square beta and so on, where Pc is the unmodulated power, that is a Vc square upon R. The expression for sinusoidal FM is Kp Emt equal to Kp Em sin omega nt equal to del phi sin omega nt, where del phi equal to Kp Em and del phi is defined as peak phase deviation and is directly proportional to the peak modulating signal. So this is also show the phasor diagram of the FM systems. Next one is the FM generation. So In FM generation, first one is vector diode modulators. We can generate the FM by use of the first vector diode modulators, second reactance modulators, and third modulator using linear integrated circuit. And last one is indirect method for narrowband and wideband generation of FM. And next one is PM generation or phase modulation generation methods. So here first one is vector diode indirect PM modulators, and next one is direct method with transistor and slope detectors, balance slope detectors, Foster Sally discriminator, ratio detector, demodulator using PLL, quadrature detector, and zero Gaussian detectors. So these are the some PM generation methods. In this diagram, so that diagram is the FM transmitter. There is a different blocks. So here modulating signal applied to the frequency modulator, and a output of this frequency modulator FC is multiplied by the frequency multiplier N1 and N2, and output of the frequency multiplier is the F equal to 30.6 megahertz. And after the third multiplier, the output of this is power amplifier, and this signal transmitted to the free space with the help of antenna, and also a crystal oscillator that is used here for the carrier frequency signal generator, and this signal is after the crystal oscillator output applied to the buffer and multiply by 2 multiplier, and this have the frequency 28.6 megahertz, and the crystal signal generated carrier signal that have the frequency 40.3 megahertz. So after the multiply by 2, that frequency will be 28.6 megahertz, and this signal is fed to the mixer, and after the mixing, and also a signal from the output of a frequency multiplier also mix here, and output of this mixer applied to the band pass filter, and output of this band pass filter is 2 megahertz, and the output of this band pass filters is fed to the discriminator tuned to 2 megahertz, and output of this is the DC correction voltage and applied to the low pass filter, and output of this low pass filter again applied to the frequency modulator. So this is the uh, frequency modulation transmitter, in which the signal is transmitted with the help of this frequency modulated transmitter to the free space with the help of antenna. Next one, indirect FM transmitter. So in this indirect FM transmitter, we have a modulating signal applied to the BMMT to integrator, and after the integration, the output of this integration applied to the balance modulator, and also a carrier oscillator generate the carrier signal, and that signal shifted by the 90-degree phase shift, and applied to the balance modulator. And next output of this modulator is applied to the summing circuit. After the summing, the output of this summing circuit, that is the FC plus del FMT, and this again multiplied by the N, and output of this frequency multiplier NFC plus N delta FMT, and then this signal is fed to the down converter, and down converter also receive a signal from the crystal oscillator, that is the high frequency carrier signal. And after the down converting, the output of this down convert applied to the class C amplifier, and class C amplifier amplify this signal to a particular level and transmit to this signal to the free space with the help of antenna. So this is the indirect FM transmitter. FM receivers. So in this diagram, that is the FM receiver diagram, the signal is received with the help of antenna, and this signal feed to the RF amplifier, and this output of amplifier signal is applied to the mixers, and also another signal that is generated by local signal applied to this mixer, and after the two signal of mixing here, the output of this mixer is have the frequency IF frequency 10.6 10.7 megahertz, and this frequency signal applied to the IF amplifier, and then to limiter and discriminator, and again by the loop of automatic frequency control AFC to the local oscillator, and output of this discriminator is the audio amplifier and de-emphasis network applied, and output of this audio amplifier and de-emphasis network is applied to the low pass filter, and low pass filter have the output in the form of original signal. So original signal received here in the output receivers, is the output receiver. So this is the block diagram of FM receiver. This block diagram show the double super heterodyne receiver. So in this super heterodyne receivers, there are many networks we use here. RF amplifier, pre-selectors, buffer, first mixer, first local oscillators, and de-emphasis network, audio amplifier, and last we have the speaker in the form of a load, or we receive the original signal at the end of the receivers. So this block diagram show the double super heterodyne receivers. It is a feedback system in super heterodyne receiver that generates a signal that has a fixed relation to the phase of a reference signal. A phase lock loop PLL circuit responds to both the frequency and phase of the input signals by changing the frequency of the voltage control oscillator until it matches to the reference input in both frequency and phase. Hence, it is a negative feedback system, except that the feedback error signal is a phase rather than a current or voltage signal, as usually the case in conventional feedback system. So here, this is the PLL block diagram in which a band pass filter, a reference signal is applied to the band pass filter here, and output of this band pass filter is applied to the multiplier network, and also a output of this multiplier is a high frequency low pass filter, and then again to loop filter, and output of these this loop filter feed to the voltage control oscillators, and again this voltage control oscillator output to the uh, multiplier. And also if we measure the output of this voltage control oscillator, so signal phase log loop to a reference here. So this is the PLL block diagram. And this is also a digital PLL block diagram. In digital PLL block diagram, the reference signal is a digital signal, and this signal applied to the digital phase detector. And this digital phase detector convert this digital signal up and down, and this signal of output of this digital phase detector feed to the counter. Counter is up and down counting. So output of this counter is feed to the digital control oscillator, or output of this digital control oscillator is the digital signal is again applied to the digital phase log detector. So this is the complete the PLL block diagram of digital systems. And what is the application of PLL? So PLL used as a data and tape synchronization, used in modems, FSK modulation, FM demodulation, frequency synthesizer, tone decoding, and frequency multiplication and divisions. So these are the some applications of phase log loop PLL. Next one is direct digital synthesis. So direct digital synthesis is a powerful technique to generate RF signals. A direct digital synthesizer operates by storing the points of a waveform in digital format and then recalling them to generate the waveform. The rate at which the synthesizer completes one waveform then determines the frequency. So that is the block diagram of direct digital synthesis. In this block diagram, the frequency information or phase increment signal applied to the phase accumulator, and also another signal, that is the clock signal, also applied to the phase accumulator, and output of this phase accumulator feed to the waveform map, ROM or chrome, and output of this is again feed to the digital to analog converter. Here the digital signal convert into the analog signal, and this analog signal is feed to the low pass filter, and this low pass filter allow the low frequency signal, and output of this low pass filter is the uh, direct digital synthesis output. So this is the block diagram of direct digital synthesis. In analog pulse modulation, next one is the pulse modulation. That is the another type of the modulation. That is the digital type modulation. So pulse modulation, in analog pulse modulation, the carrier is periodic pulse train. Okay, in analog pulse modulation, the amplitude, position, and width of the carrier pulse train are vary in continuous manner in accordance with the corresponding samples value. of message signals. Thus, in pulse modulation, information is transmitted basically in analog form, but the transmission takes place at discrete times. In the case of digital pulse modulation, the message signal is represented in a form that is discrete in both time and amplitude. The data is transmitted as a sequence of coded pulses. This type of modulation is also called pulse code modulation, PCM modulation. So that is the digital modulation. The PCM is the most widely used in the field of telecommunication engineering. So digital data transmission provide a higher levels of noise, immunity, more flexibility in the bandwidth, power trade-off possibility, and possibility of providing more security to data and EG2 implementation using large-scale integrated circuit. Now, predominant methods of pulse modulations. So there are different pulse pulse modulation methods. So first one, pulse width modulation, PWM. Second one, pulse position modulation, PPM. And next one is pulse amplitude modulation, PAM. And pulse code modulation, PCM. So this figure show the pulse width modulation, in which first signal is the analog or modulating signal. After the pulse width modulation, the second waveform show the resultant pulse width modulated waveform, in which the width of the pulse is changed. So according to the modulating signal. So in pulse width modulation, width of pulse is changed. Next one is pulse amplitude modulation. So this figure show the pulse amplitude modulated waveforms. First waveform show the modulating signals or message signal, and second show the pulse amplitude modulated output signals, in which the pulse of the amplitude is changed. So amplitude of the pulse is changed according to the modulated signal. So that is the waveform representation of the pulse amplitude modulated system. So this circuit diagram show the pulse amplitude modulation system, in which a triple IC timer IC used, and one diode and different resistance and a power supply also used here, and one capacitor C1 and C2 also used here. So we applied this circuit at the input pulse width modulated signal, and output of this circuit diagram, that is the PPM output, pulse position modulated signals. So in this waveform, that waveform show the pulse modulation techniques. So first wave show the here sine wave input, and second waveform show the pulse amplitude modulated waveform, and Next one is the pulse code modulated waveforms. So these are the different waveforms of different modulated signals. PCM offers a method of overcoming some of the disadvantage of other type of pulse modulation. In PCM, the instantaneous amplitude of the sample is represented by a binary code, resulting in a series of ones and zero or mark and space. So all pulses have the same height and same shapes. Since only ones and zero are sent, the receiver has only to detect the presence or absence of a pulse. A distorted pulse does not degrade the signal as long as the pulse can still be recognized. Hence, PCM is less sensitive to noise than other modulated systems as a PAM or PWM. So PCM is the less sensitive to the noise to other than modulation techniques. So this block diagram show the pulse code transmitter and PCM receivers. So here in this diagram, first part show the PCM transmitter, and next part, second part, show the PCM receivers. So in PCM transmitter, there is a analog input signal to apply band pass filter, and output of this band pass filter is fed to the sample and hold circuit, and the output of this sample and hold circuit, and that is the analog signal, and this signal convert to the analog to digital by the A to D converter, and after the conversion of analog to digital, the output of this A to D is the parallel data signals, and that is the digital signal, and this signal applied to the parallel to serial converter, and parallel to serial converter convert these parallel digital signals into the serial signals, and these signals, series signals, are PCM codes, and these PCM codes apply to the regenerative repeaters. And after the repeaters, the output of this, that is the serial PCM codes, and this serial PCM code applied to the regenerative repeaters, and output of this repeater is the serial PCM code. And again, this applied to serial to parallel converter. Over here, the serial signal convert into the parallel converter by the serial to parallel converter. Output of this is parallel signals and digital signals, and these digital signals convert to the analog signals again by the D to A converter, and again this output signal, that is the analog, applied to the hold circuit, and the output of this hold circuit applied to the low pass filter, or output of this low pass filter is the output signal, that is the analog signal or original signal. So at the PCM receiver output, here is the analog output signal. So this is the combination block diagram of the PCM transmitter and receiver. Next, multiplexing. So what is the multiplexing in modulation technique system? When more than one application or connection share the capacity of one link, it is called multiplexing. This results in better utilization of resources, and all typical example is many conversations over telephone lines trunk lines, wireless channels, etc. A few examples of multiplexings are TDM, that is the multiplexing system, time division multiplexing, FDM, frequency division multiplexing, WDM, wavelength division multiplexing, and CDMA, port division multiple access, port division multiple access, CDMA. So this diagram show the FDM transmitter. So in this FDM transmitter, we have the different message signal M1T, M2T, and we applied to these different signal to the subcarrier modulators, which have the frequency F1, F1, F2, and Fn. And output of these subcarrier modulator is S1T, S2T, and so on. And these all output are summing network. And after the summing, the output of this is the MBT feed to the transmitter, and output of this transmitter is the FDM signal, that is the ST. So this is the FDM transmitter, and this is the FDM receivers. So in FDM receivers, the original signal is received at the output of the different demodulators. So here FDM signal is feed to the main receivers, and which have the carrier frequency FC. Output of this main receiver is MBT, and again this output is divided in different band pass filter and applied to this different band pass filter, which have the frequency F1, F2, F3, and Fn. And output of these filters is S1, S2, and Sn. And these different filter outputs applied to the different demodulators, and output of these demodulators is the original signal or baseband signal or modulating signal at the end of the receivers. So this is the FDM receiver block diagram, and this block diagram also show the synchronous time division multiplexing transmitter, time division multiplexing TDM, in which we use two different buffers for different message signals, and output of these different buffers is scanned by a scan operation, and output of this is MCT, that is the TDM streams, and next feed to the modem, and output of this modem is the modulated TDM frames, that is the ST. So there are uh, given some frames here in second diagram, and this is the also synchronous TDM receivers in this reverse process as compared to TDM transmitter, and original signal or message signal received here at the different buffer outputs at the receiving end. So this is the analog carrier system using FDM. So here we have different 12 voice channels applied to the FDM, which have the 4 kilohertz frequency, and next the output of this FDM is 48 kilohertz 12 channels, and again applied to 5 groups to the next FDM, and output of this FDM is super group 240 kilohertz and 60 channels and 10 super groups, and again repeat this process, and last the output FDM is jumbo group, that is the 1600 16,984 megahertz frequency and 3,600 channels. This is also digital carrier system TDM. These are the some books for this topic. First one is Principle of Communication by Top Ceiling. Second one is the Analog Communication by Birla and Sharma. These are the some multi-choice questions of this topic. Now we will discuss these multi-choice questions one by one. So in first questions, in frequency modulation, option A, amplitude of the carrier remains same. Option B, frequency of the carrier varies in accordance with the modulating signal. Option C, the number of sidebands are infinite. Option D, all of the above. So here correct option is D for the frequency modulation. All options are correct. In second question, frequency deviation in FM is option A, change in carrier frequency to frequency above and below the center frequency. Option B, formation of sidebands. Option C, the variation of the instantaneous carrier frequency in proportional to the modulating signal. And D is all of the above. So for the frequency deviation, all options are correct. So here, correct answer is option D. In next questions, carrier swing is defined as option A, the total variation in frequency from the lowest to the highest point. Option B, frequency deviation above or below the carrier frequency. Option C, width of the sideband. Option D, none of the above. So for the carrier swing is defined as the total variation in frequency from the lowest to the highest point. So correct option is option A. The amount of frequency deviation in FM signal depend on option A, amplitude of the modulating signal. Option B, carrier frequency. Option C, modulating frequency. Option D, transmitter amplifier. So correct answer here, option A, amount of the frequency deviation in FM signal depend on the amplitude of the modulating signal. In next questions, drawbacks of using direct method for generation of FM signal are first, option A does not give high stability to FM signal frequency. Option B, distorted FM signal is generated due to harmonics of modulating signals. Option C, cannot be used for high power FM generations. Option D, both A and B. So correct option here is option D, in which option B and A are correct. In next questions, advantage of using direct method for generation of FM is option A, it gives high stability to FM signal frequency. Option B, distortion-free FM signal is generated. Option C, high power FM generation is possible. Option D, none of the above. So, advantage of using direct method for generation of FM signal is high power FM generation is possible. So, correct answer option C. And next questions. Drawbacks of tuned radio receiver are option A, oscillate at high frequency. Option B, selectivity is poor. Option C, bandwidth of the TRF receiver varies with incoming frequency. Option D, all of the above. So here, correct answer is option D. Drawbacks of tuned receiver are all options A, B, and C are. So option D is the correct answer. Next, sensitivity is defined as A, ability of receiver to amplify big signals. B, ability to reject unwanted signals. Option C, ability to convert incoming signal into image frequency. Option D, ability to reject noise. So sensitivity is defined as the ability to receiver to amplify big signals. So answer correct here option A. In radio receivers, varactor diode are used for option A tuning, option B demodulation, option C mixing, option D none of the above. So here in radio receiver, varactor diode are used for the tuning purpose. So here correct option is the option A. Thank you very much.